Ja, då är väl klockan ganska så precis 13.00. Så då kör vi igång igen med eftermiddagens pass. Nu blir det en presentation som handlar om rock art, machine learning och citizen science. Och den kommer att vara på engelska. Jag tror att det är för våra internationella gäster, men det går förmodligen alldeles utmärkt att ställa frågorna på svenska. Och de som presenterar är Johan Ling, som är professor i arkeologi vid Göteborgs universitet, och Niclas Hagen, som är forskningskoordinator vid Centrum för digital humaniora vid Göteborgs universitet och också vetenskapsteoretiker vid Göteborgs universitet. Välkomna!
All right. I'm going to start this presentation with a question, and that is, can data-driven science, artificial intelligence, but also citizen science help Bronze Age and rock art research in order to classify and identify rock art? And this is more or less what this presentation is about. And this presentation is then based on, first of all, a collaboration between Swedish rock art research archives, between Center for Digital Humanities, but also Chalmers data science research engineers. And I'm going to start with some background for this project, presenting the rock art material. Also, the new documentation methods we have implemented, and then the case on machine learning. In the end, Niclas Hagen is going to put some theoretical aspects on this with machine learning, humanities, and citizen science. First of all, we have in Scandinavia Europe's largest concentration of prehistoric rock art dated to the Bronze Age. A massive amount of data. And here are the most common, or the region with most dense rock art then. The region that has outermost dense rock art is in West Sweden, as you probably most of you know here. You see in the red dots are rock art sites, and we count to about 2,000 only in West Sweden here. And a site can contain between 20 or maybe up to 200 images. Here is an example of a fantastic site from Fossum Tanum, where you show warriors, boats, wagons, charioteers, animals, and antagonistic scenes. There are several examples of sites and documentations, of course, that are world famous. We have the fishing scenes. We have also the vaulters that you find the closest analogy to in the Mediterranean world, but also the lure blowers. One major problem for research and common public was that all this material, the documentation material, was scattered, spread over 50 or 60 different kind of institutions. However, with the launch of Swedish rock art research archives, this has changed. We have now scanned about 70,000 of a total of 100,000 documents and put them out on the web. We have 1 million visitors. We have very much research using our data for publication, thesis, etc., etc. And it's the only database in the world that gives full access to primary documentation. However, what we have been working on pretty hard the last couple of years is to find or enhance the documentation method. And that is with new 3D documentation methods, such as IBM, image-based modeling, and the latest laser scanning. The latter method was implemented here in West Sweden, or in Sweden, by Henrik Sedig at the Counter Administration Board in order to do full documentation of the World Heritage Site. And we have collaborated intensely with him on several research topics. The scan that he has implemented here holds an accuracy of about 0.03 millimeters and sends out 480,000 points per second. It is no doubt the documentation method it's the only scientific in that matter. Comparing to traditional documentation, it gives not only information on depth, form, and style, but also on topography. And you can measure it, you can reproduce it, it will be the same. While if you compare to, this method, it doesn't capture topography. This method, with the felt pen and plastic rubbing, you interpret what's been chopped or not. You don't get information on topography, you don't get information on depth or other features or the context. The problem with the traditional documentation methods is we can see here, for instance, when we project this, that it loses information, as you see here. The sword is considerably broader. Also, there is some feature on the head. It is the same depth, it is the same texture, it is chopped. So therefore, a very important condition for this attempt is that we use this laser data. And to summarize, we want to have so little human bias as possible when we learn the algorithms how to identify and classify rock art. The traditional documentation method has a tendency to rather reflect the contemporary documentator, as you see here. And what we're looking for is what this guy, this prehistoric man, has generated in a rock. We're not so interested in what he has done in that sense. So therefore, the aim then is to implement methods from data science, artificial intelligence, and machine learning methods. And the goal, on basis of the laser data, learn the algorithms to identify and classify rock art. And not only traditionally in terms of style and form, but also depth and texture. And that is the geological texture we're speaking about. And learn it to recognize features. As for ships, we have 10,000 ships in West Sweden only that needs to be classified. We have weapons, we have wagons, we have animals. Also, another aim is maybe to identify carving techniques and thereby different creators of rock art. How you can see how mobile certain groups or maybe also individuals are in the landscape. Looking at the data science then, I'm doing a very comprehensive summarize of Oskar Ivarsson's slides here. What we're using from that is machine learning, visualization, but also data management and computer vision. It's an interdisciplinary field with very much different features and strands. More specifically, if you look at machine learning, then we have seen examples today in the context of text, but you can use it for text, as we've shown. You use it to identify cancer cells. You use it to identify persons, animals, and species on images in video archives. So it's out in society already, whatever you want or not. So this project objectives then is with the use of the data scientific methods. We can automate the segmentation of rock art in panels with minimizing human bias. And learn the algorithms, because there exists also another project in Italy where you actually learned it with traditional documentation. And the outcome of that was really biased, actually. The data then, we have data from panels in various size and resolution. Some are really large, some are really small. The format of the 3D models is meshes consisting of edges and vertices. I will now go to some of the outcomes and not so much details on the techniques, but what we already could do now and what the algorithm is identifying, which is really important, and that is the natural features on the rock. We don't want the algorithms to interpret new rock art on that, right? So here we can see, for instance, exfoliation or vitrification detected by the algorithm. Also, directional noise caused by the ice smoothing on the rock. So here we can see, for instance, here you can see the directional noise. Here you can see the exfoliation, and it also detects the rock art in a different depth and manner. A more clear example is actually this site, which we have scanned then. Here's the interpretation by archaeologists. We scan the site, the algorithms make a depth map, and then a visualization on basis of that depth map, which is really strong according to our view, and closer to the reality than the painted version, so to speak. Here's another. I just want to highlight this scene here. You have a combat scene in the middle of this panel, and what we now can enhance with this method is, for instance, here's the interpretation of this scene before, where you argue that these combats, one of the combatants has an axe arm. His arm is ending in an axe, really strange. We scanned this, Henrik Sedig and me, and could, which resulted in that we can show that there's no ending here in this feature, that this is actually a continuous feature. And our interpretation here is also the algorithms verifying that, then also that this goes beneath this guy. And that this guy is holding and swinging a flame-hilted sword that we date to 1400 to 1300 BC. So the idea now is to further these algorithms to be able to identify weapons and boats. We have, as I said, very many boats here in West Sweden. That will help research very much. Now, traditionally, you do annotation and interpretation of a panel manually, and it's very time-consuming. So the very idea then is to learn the algorithms, as we have done here manually, to mark what we can show here is warriors from the early Bronze Age, while the boats are from a late Bronze Age. But it's a massive amount of data. I gave you a picture in the beginning. It's so many sites, there's so many features on the sites. So also what we're now implementing is citizen science, to see if we can feed this machine learning model with, first of all, we have specialist label data and unlabeled data. Then we have known classes going out to common public for classification, such as boats. This ends up in a confirmed class checked by researchers and goes into the machine again. While, on the other hand, you have unknown classes going up to researchers or high-level students for classification and goes back to confirmed classes and in the machine again. This is exactly what we've done in Zoo Universe, right, Niclas?
Yes, it is. I mean, we now come to the third word in the title, which is citizen science, and the question is, and what is citizen science? And I suspect that many of you have met this practice or phenomenon before. Somebody mentioned the word crowdsourcing earlier in one of the earlier presentations here. Well, citizen science is not a new kid on the block. There is no coincidence that we have a bird and bird watchers on the slide here, because bird watchers or ornithology were one of the first disciplines that actually engaged volunteers in the research project or in the research process. And the reason is quite simple. There is not enough scientists out in the field to cover. For example, if you study migration patterns in different animals and in birds, there's not enough scientists out there to do an inventory of migrating birds. During the last 10 years, give or take 2-3 years, there's come a digital turn, which has turned things quite a bit upside down by such platforms as Zooniverse, for example, and eBird. And painting the picture in the broad strokes, I would say that citizen science or crowdsourcing today is revolving around either time and space issues. You need people out in the field to do environmental reporting, reporting on birds and other animals, invasive species, etc. But you also have projects. Many of the projects, not all, but many of the projects on this universe revolves around big data and the issue of how to handle large, massive data sets. I would say currently that citizen science or crowdsourcing is going through, if I'm a bit nasty, a sort of hype. There's a huge amount of expectations on the policy level. which connects the aspect of engaging volunteers or engaging the public in the scientific process, a direct activation of the public, is tied to what I think Britt Staksson and Helene Lööw talked about, populism, fact resilience, fake news, etc., etc. And this is just a quotation from Carlos Meras, the Commissioner for Research and Science and Innovation. You can clearly see that he thinks that citizen science will bring scientists closer to people. My personal opinion is that the jury is still out on that question, but there are strong expectations around this practice at the moment. For me, as a theory scientist, I think that this kind of infrastructure that Johan talked about, that will be tried to implement in relationship to rock art studies, is quite interesting because it brings humanities closer to natural science. We now, traditional research within humanities, you have not been relying upon a big-scale infrastructure. And this is exactly what we're moving towards right now. In order to do the kind of research that Johan talks about, we need an infrastructure, and we need the money to build up the infrastructure. And of course, it's interesting to see what happens in terms of research practices and epistemologies within the humanities when we have archaeologists, we have citizens or the public, we have data science who collaborate with each other on the same platform. And it also brings issues in related to the notion of interdisciplinarity or transdisciplinarity. Because we not only have researchers who have to talk to each other, we have researchers who have to talk to the public and engage the public and interact with the public. But we also, in the middle of these, also have a machine learning program. So all of this, I think, as a theory of scientists, an interesting turn for humanities. What will happen when on these infrastructure? And that is a research project in itself.
It's the thing here, we should add also, it's really important in this model, I forgot to stress that, but the protocol,
yes.
Right?
Yeah.
So you have a tight protocol that the human vetting are using, produced by researchers, of course, that holds them tight. But interesting enough, if you look at Zoo Universe or other platforms, they argue that accordingly with their protocols that are really tight, the outcome of the classification holds 99.3% accuracy, which is really interesting in that sense. So it's to have a tight protocol, and then it checks also to be checked by researchers in the end, and then it feeds the database. So it's organic self-teaching system, so to speak. Okay, I think we are pretty much
You're
done.
done? Yeah. Wonderful. So we have time for questions. Thank you. Ja, har vi frågor, kommentarer? Vem är det som ansvarar för micken här? Någon fråga eller en kommentar?
Trond has a question, I can see. What?
Many questions, but I'm intrigued and I'm fascinated by the progress. But how do you? How will it work in practice?
With
the machine learning.
Well, I can't go into detail in the technical aspects of it, but that's how Oscar has to. But what it does, it learns the algorithm, what is shot or not, on basis of depth and texture. But the important thing is that it has so much information, and that the information is not biased there. And then you're able to forward it. We discussed before the possibility, for instance, to check, the dream is to see if you have a carver that is making the same image. And we know that by style, we can say, and also we have observations in terms of the eye. But how to show that? And the only means to show that is the scanner and and then that you put this in the algorithm, so it could calculate not only in terms of depth and texture, but also form and style. So that's the challenge we stand in front of. But knowing what the algorithms can do in other, cancer cells, birds. Birds are considerably more complex than rock art. Look at all the feathers they have. And there's a tendency in traditional rock art research, no, we are the only one that can interpret this. And yeah, experience is really important, but it comes back to data as well. And to use, high accurate data and find new ways of interpretation or classifications. That it doesn't stand in contrast to traditional interpretation, so to speak.
Well, you're invited to my sites.
Good. Perfekt. Tack så mycket.
Ja, bra.
Ni får